Hello, my name is Mateusz, and together with my co-authors, Masood, Xiang, Manmohan, and Masa, I would like to present our paper. In a domain generalization setting, we train our model on various training domains and evaluate it on significantly different unseen domain. Traditionally, we employ a leave-one-out evaluation protocol. Using the PAX benchmark example, we train our model on three distinct domains: cartoons, sketches, and photos. Subsequently, we evaluate its performance on the remaining domain, in this instance, the art domain. In a similar fashion, we will proceed to evaluate our model across the remaining domains like cartoon, sketch, and photo. We can train an oracle model using data from all domains. The ultimate goal of domain generalization is to bridge the gap between the model trained on all but one domain and the oracle. We drew inspiration from the research of Jinglong Ling and colleagues, who demonstrated that higher gradient signal-to-noise ratio, GSNR, correlates with better generalization. GSNR for parameter θj is defined as the squared mean of gradients of the loss function with respect to parameter θj divided by the variance of these gradients. The key insight here is that high GSNR implies small dispersion in gradient directions across training examples. This suggests that the network has identified a discriminative pattern that is likely to generalize effectively to unseen data. However, it is unclear on how to enhance the GSNR of network's parameters. Our inspiration also draws from the work of Zhe Huang and colleagues. In their research, the authors proposed a unique approach of applying dropout selectively to the most important parameters measured by the magnitude of the gradients of the loss function with respect to those parameters. This diverges from the classical method of muting random parameters selected through Bernoulli sampling. The rationale behind this novel approach is to encourage the network to explore alternative patterns that could prove valuable when confronted with previously unseen domains. In our approach, we advocate for guiding the dropout procedure by muting parameters with the highest GSNR. Our approach builds upon DropBlock, a straightforward extension of dropout designed specifically for convolutional neural networks. Traditionally, DropBlock zeroes patches of parameters by randomly selecting patch centers using Bernoulli sampling. In our variant, we opt to select patch centers based on highest GSNR. Algorithm 1 provides an overview of our approach. We begin with a forward pass to obtain the gradients needed for computing GSNR. In practice, we found that utilizing the empirical mean and variance from the current batch yields effective results. We then mask parameters with the highest GSNR for zeroing. Following common practice, we introduce another mask to determine whether dropout should be applied in a given iteration. This mask is generated using Bernoulli sampling, and its modeling parameter is denoted as pGSNR. When using ResNet 18, we can see that the dropout procedure can be applied at multiple spots, after the first ResNet block, the second, the third, the last, or a combination of these. To identify the most effective placement and dropout probability, we conducted an exhaustive grid search testing various combinations. The histogram of this extensive experiment, involving approximately 1,300 models, reveals that simply guessing the optimal placement and probability can lead to suboptimal results. Because of this, we believed it would be advantageous if the network learned both the placement and probability autonomously. The parameter governing this process is pGSNR, as mentioned earlier. However, we cannot compute the derivative of the loss function with respect to pGSNR due to the non-differentiable nature of Bernoulli sampling. To circumvent this challenge, we generate the mask by sampling from a uniform distribution and applying a scaled sigmoid function. This approach enables us to calculate the derivative, thereby allowing the parameter pGSNR to be learned. Our learning-to-learn procedure, which we base on MetaSGD, is illustrated in Algorithm 2. Here you can observe the plots depicting the learned probabilities for various ResNet blocks and PAX domains. We conducted exhaustive experiments on commonly used benchmarks where our method obtains promising results. Thank you for your time. Please join us at our poster session on Wednesday. I'm also happy to meet for a coffee during other time slots.